Good morning, everyone. Welcome to week 3 of our linear algebra course, MATH13217. Today, we will delve deeper into our linear algebra journey and will introduce something very essential, which is called the determinant. We'll begin with acknowledgement of country. We respectfully acknowledge the traditional custodian on the land of the lands on which we work and learn. We pay respect to First Nations people, the elders past, present, emerging, for they hold the memories, the tradition, the culture, and hopes of Aboriginal and Torres Strait Islanders people. Aboriginal and Torres Strait Islander people should be aware that this course may contain images, voices, and names of the deceased person. That's well. So a quick recap on what we did last week. So we talked about metric multiplication, when you multiply the matrices, provided the rows and column numbers were assigned. We also verified in general that A times B is not equal to B times A. And some rules of metric multiplication, right? The commutative rule, the multiplication distributive rule, association rule, and other properties of multiplication of matrices. Okay, today we introduce something that is called determinant. So what is a determinant? So first of all, we should understand that okay, so determinant of order n is a scalar. So that's very important. Is a scalar number that is associated with an n cross n matrix. So other thing to note that the determinant is only possible for a square matrix, whose number of rows and columns are the same. The determinant, as it starts from D, we have adopted the number D, which is DETA, determinant of A, or the absolute value thing, but we don't call it absolute value, we call it determinant A, is where you put the square lines and not the metric form, but the square lines. It is a single numerical value which is used when calculating the inverse or when solving system of linear equation. Okay. So what will happen eventually that we will talk about, okay, let me introduce a bit here. If the system of equation is AX is equal to B, but A is a coefficient metric and B is the constant on the right-hand side, okay, then we will say that X will be A inverse B. Same like our normal algebra, abstract algebra, when you have something like 2x is equal to 3, x is 1 over 2 times 3, or sometimes we say it 2 power minus 1 times 3. Up here, minus 1 is not the power, it's the inverse. Okay, how do you find the inverse of a matrix? That is adjoint of A divided by mod A. Right, that mode is the determinant of A. So that is a very essential, to solve system of linear equation. When it's a system of linear equation, we are talking about more than one equation, linear equation. So just to clarify understanding, linear equation means the equation whose variables, doesn't matter how many, it could be 1, 2, 3, n number of variables, at the maximum power 1. If it goes 2, it's called quadratic. It says 3, then it's called cubical, and so on. Okay. So again, system of linear equation, more than one equation, all variables have power 1. If you wanted to solve it, find the solution, find the unknown, the variable x, y, z, or x1, x2, x3, xn, then this is how you write them. Ax is equal to b and x will be A inverse b. In order to find A inverse, you need adjoint A. Again, I'll describe when it comes in the upcoming session, what is adjoint A, but this is where the determinant is very essential. Okay, so n is equal to 1, determinant is just A1, the number itself. the determinant can be expressed in two different forms, depending on the expansion of D either by a row or by a column. Okay, so again, when it comes to 3 by 3 or 2 by 2, it will make more sense, right? But in general, the definition of determinant, right? If you pick up the row expansion, so it's multiplication of AI1 times by CI1, which is a cofactor. Again, I'll explain what is a cofactor, plus AI2, CI2 up to AI and CN. In general, this is how it's written in the sigma form. Similarly, if you go with the column expansion, you will say A1J, C1J. Please observe here that when you're talking about multiplication of matrices, it was Aij and Bjk. The suffix, right, in multiplication was aligned. Up here is the same because you are multiplying the element with a cofactor. Okay. Now, what is a cofactor? Cofactor is minus 1 power I plus j times by its minor, mij. What is a minor? You eliminate the rows and column containing that number. This could be a heavy slide to understand with a lot of IJ and new terminology, but we take an example and things will get more clear. Mij is called the minor of Aij, which is also a determinant of order, one lesser order. So if it was 3 by 3, minor is a 2 by 2. If it was 2 by 2, minor is 1 by 1, right? If you remove the ith entry and jth column, ith row and jth column, right? Like I said, it will not make too much sense right now. It's better we dwell into an example and things will get start clear. Okay, so if we talk about a 2 by 2 matrix, so let's talk about a 2 by 2 matrix. So let me pick up a metric M. One, 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 two, two, one, two, two, right? So if you go to the definition of determinant, AI1, CI1, AI2, CI2, right? So up here, D, the determinant can be written as A11, C11, A12, C12. First element, see the first element A11 with its cofactor, plus second element with its cofactor. Okay. Now, you can write in general that the determinant D will be AI1 because you're talking about, this thing CI1, AI2, CI2. Okay, this you can talk. Up here, we have taken I is equal to 1. Okay, now what are C11? Okay, C is a cofactor. The definition of cofactor says is minus 1 power I plus j. So if you have this I and j, it's I plus j here times by its minor. Okay, so C11, if I pick up this metric, okay, so C11 will represent the cofactor of A11. Okay, so what you should do, let me take some pen. When I'm talking about cofactor of A11, I'm multiplying by its minor. Now, what is minor? M11. What is it? You eliminate the rows and column containing that element. If I'm talking about minor of C11, right? The cofactor C11. So I'm talking about M11. That is the minor for A11. Everything the same suffixes, right? I will eliminate first row, first column, 1, 1. First row, first column. Whatever left is this only number because minus 1 power 1 plus 1 will become minus 1 square. And so it's plus 1. Okay. Another one. Let me take purple. Okay. If I talk about C12, that is the cofactor of A12. Okay, how do you find the cofactor of A12? So you start with minus 1 power 1 plus 2, this element, I plus j, 1 plus 2 here, times by the minor of A12. Now, how do you find the minor of A12? I'll write it here again. A11, A12, 21. Okay, when I'm talking about the minor of A12, I will eliminate the first row, second column, everything containing A12. What is left over is A21. Okay, where does this minus come from? Because here is minus 1 power 3, minus 1 power odd, right? That will give you a minus. Okay, so finally, the determinant of A11, A12, 21, 22, as per this definition, which I already written here, what we needed was the C11, which is A22, and C12, which is minus A2, and just plug it back in. Now, for 2 by 2, you don't have to go this complicated. Okay, for 2 by 2, what you do? Okay, so I'll pick up a normal metric, 1, 5, 7, 9. If you want to find this determinant, it's very simple. Now, by this time, you would have understood the principal diagonal, which is 1 times 9, minus the secondary diagonal, 7 times 5. So 9 minus 35, and that would be minus 26. That's the determinant. But this is a process, because slowly we will build up on this process. Then we'll go for 3 by 3 determinant. Then we'll go with 4 by 4 determinant. I don't think we will need in this course 5 by 5, but it can happen if you're talking about 5 variables. Electronic circuits, right? I1, I2, I3, I4, I5, or for example, something with 4 CMYK, right? When you go for color printing, right? Cyan, magenta, yellow, and black. That combination, let's say 0.2% of C, 0.1% of this will create any number. I'm sure if you ever go to Bunnings and you ask for any shade, they will have the base color. They will just add this some amount of the CMYK in relative proportion, and that will create all the numbers in that catalog they have, all the colors, right? Just because of some combination, some amount of CMYK, right? Now, sometimes we know the outcome. We know that we need that shade 4 of that purple color, which is not purple, but purple with something else, right? How much of each of this would we use? And this is why you try to find the values of the unknown. How much of C, how much of M, how much of yellow, how much of black, CMYK, that will produce purple category 4, right? Or red category 7. When you go that there is a shade card, right? So this is how there is a math, there is a linear algebra behind it. Okay. Right. So again, there is an example, but like I said, you don't have to go this complicated because even in the exam or wherever you have to deal with it, no one will say do it with the help of cofactor or minor only. They will only ask you find the determinant. If it is 2 by 2, obviously you will go for the shortcut way, right? So let me do this one here. So we got A, sorry. A is determinant of 4, 3, 1, 2. Like I said, multiply the principal. So 4 times 2, subtract the secondary. That is 5. So determinant is 5. But still, I wanted to introduce the method which we can build up, right? So slowly, let's look at that. Okay. So what would be our definition, the determinant, right? If you can recall, it's AI1, CI1, AI2, CI2. If I set my I is equal to 1, you could set as 2 as well. Then my determinant will be A11, C11, A12, C12. Now, I really expect you to have mastered the concept that we learn in week 1 and 2. If not, don't go further until you understand what I'm saying. What is A1 to A2 to? If you're not even sure of that, then please go back and clear those concepts so week 3 content makes sense. If you're still struggling with what is A11, A12, or A1 and what does 1 and n means, then you won't understand any of this. So it's better you stop it here, go back and just clear those concepts and come back here. Okay, so what we need in order to find the determinant, we need C11 and C12. Okay, right. So C11, as per the definition, what is Cij? Minus 1 power I plus j times by a by j. So if I'm saying 1, 1, that means minus 1 power 1 plus 1, M11. Now, what is M11? If I'm talking about M11, I'll use a different color. Okay, right? Then I'm talking about A11 minor. In order to find A11 minor, I will eliminate the rows and column containing A11, and that will only give me 2, and that's why it's here, right? Minus 1 square, so that is plus 1. So C11, capital C11 is A22, and that gives you 2, okay? Now, let me go for some green color. If I'm talking about C12, then I'm talking about the cofactor of element A12. So minus 1 power 1 plus 2, M12. Now, what is M12? That is a minor of this. So you eliminate the rows and column containing that element. So first row, second column gone. That will leave you with 1 here. Minus 1 power 1 plus 2. So minus 1 power 3 times 1. And that gives you minus 1. Okay, so that is the C12 element. Now I clear my extra drawing, so writing makes sense. Right, now D, which is the determinant of 4, 3, 1, 2, just written in the square lines, straight lines. That's the definition. A11, C11, A12, C12. Plug in the element C12's value, C11 value, and you'll have phi, which we already got from a lot quicker way. So like I said earlier, just for 2 by 2, you don't have to go this complicated. Simply principal diagonal element multiplication minus the secondary diagonal. Okay. Now, since we got a bit of understanding of our 2 by 2, we will now go to our 3 by 3 determinant. So we now talk about 3 by 3 determinant. Of course, there is a shortcut for that as well, but we'll do it both. We will do it with the traditional way, the math, the definition way, and we'll do it with the shortcut way. Okay. So what we do, if you want to find the determinant of a 3 by 3 metric, you extend the first and second column. So you write the matrix, then this is the first column again. This is the second column. Okay, so you're talking about 5 columns. Then what you do, you took all the principal diagonals. Okay, so you got this red arrow second, red arrow third. And then you go for all the secondary diagonal elements. So that's all the blue arrow. Red are plus, blue is minus. Okay, so what we do, A11, A12, A33. A11, A22, A33, they are multiplied. Plus A11, A22, 33, that's this element. Plus A12, 23, and 31, that's the second element. A13, 21, and 32. The principal diagonal elements are multiplied together and added. Now subtract the secondary diagonal elements. So 1, 3, 2, 2, 3, 1. 1, 1, 2, 3, 3, 2. And 1, 2, 2, 1, 3, 3. Okay. Doesn't matter how you write it, but these three elements are subtracted. Okay. Let's look at an example. What we do, 1, 2, 3, 4, 5, 6, 7, 8, 9. If that's the metric, if we have, we extend two rows. We write 1, 2, 4, 5, 7, 8. First two columns are extended. Okay, now what we do? The red and blue, the principals are multiplied together. So what we will do here, 1, 5, 9, they are multiplied. 2, 6, 7 are multiplied. 3, 4, 8 are multiplied and added together. Then the blue one, 3, 5, 7, 1, 6, 8, and 2, 4, 9 is being subtracted. And that's it. Simplify that, and the answer is 18. Again, 3 by 3 is very simple. Multiply the principal diagonal elements. Extend two column. That's the first thing. Once you extend it, principal diagonals are multiplied, secondary are subtracted. Now let's look at our traditional, okay, what would be our, okay, before we go further, I think I should have written it here. Okay. Right further, up here. Okay. If I wanted to do it with the definition, okay, what it should be, the D will be AI1 CI1 plus AI2 CI2 AI3 CI3. If I let my I is equal to 1, then I'm talking about D is equal to A11 C11 A12 C12 A13 C13. Okay, now if I do C11, it is minus 1 power 1 plus 1 times by M11. Now, what is M11? The minor of A11. How do you find the minor? You eliminate the first row, first column, because you're talking about 1, 1. So this is minus 1 square. It's a determinant of 2 by 2 because the original was 3 by 3. You eliminate the rows and column containing A11. Okay, so what you got? Sorry. Okay. Okay, so minus 1 power 2, we are talking about A 2 to A23, A3 to A33. Okay, so that will be A2233 minus A2332. This is C11. Okay, if I wanted to go with C12, as I need that here, minus 1 power 1 plus 2 times by M12. So that is minus 1. M12 is the minor of A12. So you eliminate the rows and column containing A12. You remove this. So that will be a determinant A21, 23, A31, A33. Okay, so minus 1, when you expand it, 2133 minus A3123. So that will be A31, A23 minus A21, A33. Okay, then we go with C13. Minus 1 power 1 plus 3 times by M13. That's the minor of A13. So eliminate the rows and column containing A13. So that will be 2122, 3132. And that will give you A2132 minus A31, A22. Having obtained them like 1, 2, and 3, once you plug them back into equation 1 and simplify, you will obtain the same value as this. Please learn both the way using cofactor, which we done, which obviously seems a bit longer, or the shortcut method. Okay. Okay. Now, determinant can be, obtained from any rows or column. The expansion can be made with any rows or column, not necessarily the first row or second row. Anywhere. You can start from the last fourth row as well, or fourth column as well, right? As long as you are using this correct notion of, because your I can be any row, your J could be any column. Okay. So if you got a determinant where you only got, the principal diagonal elements, that means everything else is 0. Everything else is 0, 0, right? Then the determinant is the multiplication of the principal diagonal element. If everything else is 0, right? Then we got a special type, um, where we are either talking about the upper triangular or the lower triangular. In that instance, again, the determinant is the multiplication of this element. And that's very easy to prove. And that's very easy to prove. Why? Okay. If you start from the expansion using the first column, right? How would you write it? The jth column, j is equal to 1. So that will be A11, C11, 1. Then A21, C21, and keep going, right? So you'll only focus here because these all elements are 0. So 0 times any cofactor will be all 0. So then you're just focusing on this times by its cofactor, right? When you talk about the cofactor, again, you are dealing there. Again, these elements are 0. So when you talk about the cofactor of A22, then you are talking about the minor containing A33, and then that's 0, and then that will go to A44. So eventually, of course, it's an iterative process, but you will end up getting the same multiplication of the diagonal elements and nothing else, because everything else is 0. Right. So we will now talk about 4 by 4. Okay. Journey begins. With the 4 by 4, just an note, it's not the shortcut way of 3 by 4. There could be something, but I haven't come across. But the 3 by 3 is a proven shortcut. It works that way. 4 by 4, I don't think it works that way, right? I mean, you guys can be the explorer, and find some technique on your own. That's also possible. Okay, so we try that one. You can see the space that I have. I think I got good space. Okay. I got, I think, 1, 2, 3. Couple of sides. Good. Okay. So I have kept some space so I can play using this area. I like it that way. Okay. So let's go with, first of all, so if I go with the definition, how it should be. So the determinant D will be, as per the definition, AI1, CI1, AI2, CI2, AI3, CI3, AI4, CI4. Now you can set your I as anything. I'll set it as 1. So my determinant D will be A11, C11, A12, C12, A13, C13, and A14, C14. Okay. Now let's find out everything. Okay. C11. Follow the definition. And it's all about practice, you know. I will do the same determinant expansion of 4 by 4 using various different rows and columns. Okay. So the definition says -1 power 1 plus 1 M11. What is M11? This is -1 power 2 is positive. So M11 is the M11 is the cofactor of A11. So what is a cofactor of A1? You remove the row and column containing A11. So that will be this determinant, the 3 by 3 determinant. Remember, the minor will be 1 degree lesser than the actual one. So that will be a determinant. Eliminate this, okay? -1, 2, 1, 2, 3, 2, 0, 5, 2. Okay. Again, how do you expand it? So there you can talk about that shortcut way. Okay. So you can extend that -1, 2, 2, 3, and 0, 5. Okay. And then multiply the principal diagonals. So -6, I would put a bracket just so I know that I'm adding the principal and subtracting the secondary. 2, 2, so that's a 0, 1, 2, 5, so that's a 10. And then subtract 0, -10, and 8. So that's like 4, -2, so that's a 6. Okay, so my C11 is 6. Then I go with C12, then I go with C13, and then I go with C14. Okay, the more you practice, the better you will be. Okay, I'll do C12 -1 power 1 plus 2. C12 is the metric. And the minor of A12. So that will be 3, 2, 1, 1, 3, 2, 4, 5, 2. So that's a minus. Now I don't want to confuse you, but there is another way of expanding the determinant as well, a bit quickly, but let's stick to what we have learned. So 3, 2, 1, 1, 3, 2, 4, 5, 2, 3, 2, 1, 3, 4, 5. That's 18 plus 16 plus 5 minus 12 plus 30 plus 4, 18 plus 16, that's 34, 39 minus 46, and that's minus 7. There is a 7 waiting outside, so that becomes plus 7. Okay, then you go for the next C13. Okay, and then you go with the next C14. Okay, C13 and C14. Okay, and that I'll leave it to you. Yeah, just practice that. I'll post the recording here and I want you to practice it. Okay, so with the same calculation, we got our C13 as minus 2. And C14 is minus 7. So what we do, we use this equation, plug in all the values of C11, C12, 13, 14, plug in the numbers, and we get our final answer of determinant. Okay, so I'll go with blue, right? So determinant D will be A11, which is 2, C11, that was 6, plus 1 times C12, C12 is, what do you got? It's here somewhere, isn't it? 7, plus 3 times minus 2, oops, plus 1 time minus 7. Plus 7 minus 7 gone. 12 minus 6 is 6. So that is your determinant at 6. Okay. Good. So this is how you obtain a 4 by 4 determinant. Okay. Okay, so that was one way of dealing the determinant of 4 by 4. But like I explained it earlier, that's not the only way. You can pick up any row, any column, and you'll still have the same answer. Okay. So our answer was 6, if I can recall it correctly. Yeah, the determinant was 6. Okay. So let's do it with some other, other rows and columns. So can you guess what should be my preference in this instance? I would go with the 4th row. Reason, there is a 0. If there were 2 0 in a row or column, that will be my priority number 1. If there are 3, definitely that's my priority, right? Utmost priority. If there are 3 zeros in a row or column, that's where I'm expanding from. Okay, and if there are 4 zeros in a row or column, I don't need to do anything. The answer is 0, the determinant is 0, because it contains a row or column with all the zeros, right? So in our instance, I can see the 4th row has a second element 0, so I'll start from there. Okay, so the determinant B the determinant B is, I'm using the 4th row. Okay, so A 41 C41, A 42 C42, A43C43 and A44C4. If you want, I'll write one more steps. A41, that is 4 times C41. This is 0 times C42. Such a blessing, 0 times something. So I would not worry about finding a cofactor. So rather than finding 4 cofactor like we just did, you are getting the same, you should be getting the same answer with only 3 cofactor. Okay. 5 times C43 and 2 times C44. So let's find out C41, C42. Sorry, C43 and 4442. We don't have to worry about. Doesn't matter whatever it is, times by 0, so it will be 0. Why would you spend your time? Okay. C41 minus 1 power 4 plus 1. C41 is a 4th row, first column. So I would delete or eliminate that. It will remain 131 minus 121, 232. You can pause the recording and calculate here. Okay. All of them, then go with C42. That's minus 1 power 4 plus 2. That's a metric eliminating, sorry, 4-3. That's what I'm interested in rather than 4-2. 4-3. So 4th row, 3rd column. So 2, 1, 1, 3 minus 1, 1, and 1, 2, 2. And similarly, C44, that's minus 1 power 4 plus 4. 4th row, 4th column, 2, 1, 3, 3 minus 1, 2, 1, 2, 3. Okay, 4th row. Yes, you might make mistakes. That is perfectly fine. What happens sometimes that you are thinking a bit ahead or behind than what you're writing. Right? So there's a bit of gap in your thinking and writing steps, and that's why mostly you will make mistake. Okay, so impose it here, calculate all these 3 values, and then play it, and your answer should verify. Right, so this is how you obtain C41, C43, and C44. Like I mentioned, don't worry about C42 because that will be times by 0. So finally, your determinant D, which should give you the same result 6, but we are just checking it. 4 times minus 6 plus 5 times 6 plus 2 times 0, 30 minus 24. That will be 6. Happy 6, yeah. Happy 6, very happy 6. It should be the same. It's just picking up correct calculation and realizing that you could get away with only 3 cofactors rather than 4. The steps that I have done, don't worry about it. I know some other technique, which I don't want to confuse you now, maybe some other time. But follow this technique of extending column 1 and 2, and then cross multiplication of principal diagonal minus second diagonal. Just focus on the answer of C41, C43, and C44. As long as they are correct, then it's correct. Even I did a bit of mistake and typo. It happens. It's perfectly fine. But if you pick it up, that's even better. Right. So I left some empty slides. If you know, you can play with whatever you like. You can go with the 4th column expansion. So that will be this 1 times the cofactor, and then this one, then 2 and 2. Yeah, play with it. Right. I wanted to quickly take you to this website, which is some real world application of determinant of a metric. It's a nice article, and it is a hard question, and the Alexander really responded well. Determining whether metric is inverse or not. That's what I said earlier. The characteristic polynomial enhances eigenvalue. It's a very good read. Of course, It will take a lot of time, so I wouldn't do everything now. But that guy has really, really gone beyond to respond to this question. It makes fun. You should know why you're learning, because if, of course, you are a teacher, right? Future teacher or already a teacher. If your students ask you, why are we learning it? And you say, no, sorry, as a part of your curriculum, that you have to. I mean, that is not great. Yeah, you should know. It will make more fun, right? They will enjoy a bit more. So read this article. Just, what I did, that some real type, real life example or application of determinant comes up. Read a few. I got this one, especially the response from Alexander. It's really, really awesome. Okay. And it's been there for a while. It's been there for the last 6 years. Yeah. Okay. Right. Now we talk about general properties of determinant. So if we interchange any two rows of a determinant, we get a negative sign. Okay, sometimes doing that is really helpful. I'll tell you where and how. Okay, say for example, if I interchange first row with second row, all the elements, of course, yeah, my new D dash is not inverse or transpose or anything, yeah, D dash is the new metric, right, which will be minus D. Okay, this is a very important property. The most important property is this. Okay? Addition or subtraction of a multiple of a row to another row does not change the value of determinant. Okay, so what it means, let's say you got a metric D, right? Now you change your row 2 as the previous row plus 3 times of row 1, right? I'll explain using the example in the next slide, but if you do that, so row 2, now it is replaced by the previous row 2 plus 3 times of row 1, then the value D dash still remains the same. It does not alter the value. It's a phenomenon property. We'll use it many times. Yeah. Next, multiplication of a row by a constant multiplies the value of the determinant by that constant lambda. Why lambda? Because we wanted to keep the multiple separate from the normal alphabet. You don't want to talk about A times A. I mean, what it sounds is not clear. But the moment I say lambda times A, we are saying, oh, lambda is a constant and A is a metric. Yeah. So what we are saying, if you have row 2 times by 2, then the new metric D dash will be 2 times the original metric D. Okay. Same or proportional rows render the value of determinant to 0. What we are saying here. So if you got a metric D, which has rows like this 1, 2, 3, 1, 2, 3, and 4, 5, 6, the metric is 0 because it got the same row 1 and 2. Or even the proportional row. So what we mean by proportional? If a metric is 1, 2, 3, 5, 10, 15, and 4, 5, 6, then it's still 0. Very simple. It looks like up here, our second row is 5 times the first row. So if you follow this property, right, this D is 5 times the original 1, 2, 3, 1, 2, 3, 4, 5, 6, and then 2 rows being same, the answer will be 0. Right, let's look at some row operations. Okay. So let's pick an example of each. Interchange of 2 rows change the sign of a determinant. We can pick up the general example like A, B, C, D, E, F, or DHI, If that's not fun, let's pick up some numerical example because that we can connect very easily. Yeah. So let's pick up 1, 2, 3. minus 126 and 789. If I swap it with some another determinant, so what we are saying, d dash, let's swap this to. Then second row becomes first. You can obtain the value, this determinant value is 6. Yeah. Let me focus on obtaining the new determinant d dash value. Okay. So extend that minus 1, 2, 1, 2, 7, and 8. So that is minus 18 plus 42 plus 48 minus 84, 84, 24 negative, and plus 18. Right, 42 plus 48 is 90 minus 18 is 72 minus 84 minus 24 is 60 plus 18, 78, 72 minus 78, that is minus 6. So d dash is minus 6, so d dash is minus d. If you swap 0, you get a negative sign. It changes the sign of the determinant. Simple one. Okay. Next, addition or subtraction of a multiple of a row to another row does not change the value of a determinant. I can give you a numerical example as well, or I can provide you a theoretical example. Okay. Let me provide you in general example. Okay, and then I'll provide you. Okay, so slide 21. I'll copy this. I'll give an example of both. I'll paste it here. Good. One more space. Good. Yes. Right. So let's go for in general. So let me pick up a determinant D. Let's start with in general, irrespective of the value, right? So A11, A12, 13, 21, 22, 23, 31, 32, 33. Okay. My D dash, what I'm doing is my row 2 is now old row 2 plus 2 times R1. I'm multiplying by row 1 by 2 and adding it to the second one. So the first one doesn't change. A11, A12, 13, A21 plus 2A11, A22 plus 2A12, A23 plus 2A13, and the third one doesn't change. Now I can split this into two parts. Okay, I can split this into two parts. Same like metric addition, you know, consider everything else as 0. So A11, A12, A13, A21, A22, A23, 31, 32, 33, plus 0, 0, 0, 2A11, 2A12, 2A13, A31, A3, oh, sorry, 0, 0, 0. Right? You got two matrices, rows as 0, that will be treated as 0, and you obtain the same determinant. Okay, simple. If you go for the numerical example, then let's go with the numerical example. Okay, so let's pick up the metric D. Let's stick to the same determinant. That is 1, 2, 3 minus 1, 2, 6 and 7, 8, 9. You know its value is 6, right? What I'm doing in D dash, I'm changing my row 2 as previous row 2 plus 2R1. So my D dash, I'll start here because I need some space. So my D dash, row 1 doesn't change, row 3 doesn't change, row 2, it was minus 1. I'm adding 2 times of 1. So minus 1 plus 2 becomes positive 1. It was 2. The second element was 2. I'm adding 2 times 2 plus 2. So that will be 6. It was 6 in the third element. I'm adding 6 plus 3 times of 2. So that becomes 12. If you're still not clear, I can explain it here. What I have done, row 2 plus 2 times of 1. The next element is 2 plus 2 times of 2. The third element is 6 plus 2 times of 3. Right? And now I expand it. Now I will expand it. Okay. So 1, 2, 3, 1, 6, 12, 7, 8, 9, 1, 2, 1, 6, 7, 8. Okay. What you got? 54 plus 24 times 7, 120 and 48, 168. 168, yep. Plus 24 minus 18 times 7 or 42 times 3, 126. Yes, 126 plus 96 plus 18. So I sometimes murmur to myself because my first language was not English. So I know all this number in a different language. So this is what my brain is wired as, yeah? So if you add them up, 4 plus 8 plus 4, so that's a 16, carry 1, 3, 3 plus 6 is 9, 9 plus 5 is 14, so 4, carry 1. So that will be 246 minus 6 plus 6 plus 8, so that's a 20, 0, carry 2. So 10, 2, 12, 14, carry 1, so 2, 14. That's 6, so your D dash is 6, which is the same as D, and this is what we wanted. The value does not change. Awesome. Awesome. It's such a great property. I'll tell you how we will use it pretty soon. Okay. Okay. Multiplication of a row by a constant lambda multiplies the value of a determinant by lambda. Okay. So let's pick up the same example. All right. Here. D, which was minus 1. Sorry, that was 1, not minus 1. 1, 2, 3, minus 1, 2, 6, 7, 8, 9. Our D was 6. If I take my D dash as row 1 by 2, so minus 2, 4, and 6, minus 1, 2, 6, 7, 8, 9, and obtain that D dash, that should be 12. Yes, so minus 2 and 4, minus 1 and 2, 7 and 8. You can easily verify. Let's do it. So minus 36 plus 126 minus 48 minus 84, 96, and 36. Okay, so what we got? 126 minus 36. Can we say it 90? 90 minus 48. That's 42 minus, what we got? Minus 12 minus 36 minus 48. Did I do it right? 126 minus 38, 90, 90 minus, yes, it should And 1, 2, 3, 2, 4, 6. That should result in. Ah, damn. Sorry. That one is plus 2. So that's 36. So that should change. And that should change as well. Okay. 2, 4, 6, 2, 4 minus 1, 2, 6 minus 1, 2, 7, 8, 9, 7, 8. Okay. Let me do it again. Okay. So that's 36 plus 168 minus 24 minus 84, 96, 36. That's not 48, 84, 96, and 46. Okay. So that will be 168 minus 48 is 120 plus 36 is 156 minus 96 minus 36, that's 60 plus 84. 60 plus 84 is 144. And the answer is 12, which is 2 times 6. So D dash is 2 times D. Why that happened? Because I multiplied row 1 by 2. Okay, if I would have multiplied by 3, then the new D dash will be 3 times the previous. Okay. This one is very easy to prove, so I'm not going to prove it. What we are saying here is same or the proportional row will, yield an output of 0, right? So you can pick up any D, like 1, 2, 3, minus 1, minus 2, minus 3, and 7, 8, 9, and see the value will be 0 once you expand it. Or you could have gone for 1, 2, 3, 5, 10, 15. Keep the number smaller. Go for 2, 4, 6. Yeah, because we are just verifying the property. Y increasing, that should be 0 as well. I'll leave it to you guys. Yeah, just check that. I don't like you use the word homework. I mean that. Just check. Just check that. Right. So this is the time we use those property and apply. So we have seen how difficult it was to deal with this 4 by 4, especially if we don't realize that there is a 0 and we use it, right? Then it was very, very difficult. Okay. In the second approach, what we did, we utilized the 0 and make our calculation a bit shorter, right? How about we can produce more 0? Can we do it? Yes, there is a possibility. Not always is possible, but there is a possibility. Most of the cases, yes, you can bring more zeros. Sometimes it's not feasible to bring more zeros, but we don't go. Yes, for us, yes, it's possible that you can get more zeros. Okay. How will it help you? Like I explained in the second approach, that 1 0 multiplied by any cofactor, you don't have to worry about it. Don't worry about finding that cofactor. So more number of 0, the more number of cofactor you don't have to worry about. Okay, so look at the ways how you can have more 0 in one row or column. If that's not possible or that brings a lot of fraction or things, then have more 0 anywhere in the determinant. That's also helpful, right? So what we do, I call this metric A. Now what I do, you have to look for the things, how you can have more. Just observe it. Observe it and think of how you can have more zeros. Okay, I'll start like this. My row 3, I will change it as previous row 3 minus 2 times row 1. Why? Because I got a 2 here. If I times it by minus 2, that will become minus 2. See? This 2, 1 and 1. This is how you should select. So in one operation, you'll have 2 zeros. So what will be my new matrix A? Sorry, determinant. See, whatever does not change, write them first. Only row 3 is changing. Row 1, 2, and 4, it's the same. So 2, 1, 3, 1, 3 minus 1, 2, 1, 4, 0, 5, 2. It was 1. I times this by minus 2. So 1 minus 4, that will give me minus 3. This is 0. This is why we perform the operation. 3 minus 6, that's minus 3, and this is 0. Great. We bring to 0. Now, you will not do any operation on row 3. You will use row 3 to perform some operation on the other rows. Okay? You can also go with a column operation. It still remains the same. Not necessarily row operation only, column operations. Okay? Right. So, if you observe column 1 and column 3, both has a minus 3. If I subtract one from the other, I'll have one more 0. So what we do? Change column 3 into column 3 minus column 1. So the new determinant A, what does not change? Column 1, 2, and 4. Copy them first. So 2, 3 minus 3, 4. 1 minus 1, 0, 0. 1, 1, 0, 2. I'm having C3 minus C1. So column 3 was 2, 3 minus 2, that's 1. 2 minus 3 is minus 1. This is 0. And this is 5 minus, sorry, what am I doing? 3 minus 2, yep, 2 minus 3 minus 1, that's a 0, and that's a 1. Okay. Now I got 3 0 in a row, right? Can you bring more zeros? Think about it. Think about it. If you can, do it before you proceed further. I think I can. I got minus 1 and 1. So how about I do my row 1 as previous row 1 plus row 2. Because I got 1 and minus 1. So it will be a lot easier if I have more number of 0. Okay. Then my determinant A, row 1 is changing. So skip that, write everything else. 3 minus 1 minus 1, 1. Minus 3, 0, 0, 0. 4, 0, 1, 2. That is 5. This is 0, this is 0, and this is 2. I can still bring some more zeros. I can still bring some more zeros. The more the better. Always the more the better. How can I bring it? I got this element. I got this element as 2, this element as 2. Right? If I subtract it here, I'll change it row 4. See, I got 2 zeros in row 1. If I do anything in row 1, the zeros will be gone because this is 1, right? So my next operation will be using row 1, but on row 4. Okay, so row 4 is previous row 4 minus row 1. Okay, so my determinant A, row 4 changes, everything else same. So 5, 0, 0, 2, 3 minus 1 minus 1, 1. Minus 3, 0, 0, 0. And this is 4 minus 5, so minus 1. 0 minus 0 is 0. 1 minus 0 is 1. And that is 0. I think I got enough number of 0. You might still can think of getting some more. You know, you can still change your column 1 You don't have to. See, if you ask me how many zeros you need, depends. No straight answer. The more the better. But if you are taking too much time in bringing more zero, you could have literally stopped at this stage. Once you achieve 3 zeros, that's it. Just stop and do the calculation. Right? I'm just showing you further how many zeros can you bring. I'll do one more operation, then I'll stop. But you could have literally stopped here. That's it. And then go for the expansion, because then it doesn't help you so much getting more zeros. Okay. I'll just do it so I'll you feel like how it's done. Okay. So what I was saying, my column 1 will be column 1 plus column 3. So the new determinant A, everything else same. So 0, 0, 2, minus 1, minus 1, 1, 0, 0, 1, sorry, 0, 0, 0, 0, 1, 0, adding it. So that's a 5, that's a 2, that's a minus 3, and that's a 0. Okay, again, you can keep going and bringing more and more zero, right? But that's not the point. The point is we need some number of zero. We got it. Moment we think we have got enough, we will stop it. So I'll just copy this determinant. 5, 0, 0, 2, 2 minus 1 minus 1, 1, minus 3, 0, 0, 0, and 0, 0, 1, 0. Now you've got a lot of choices. What are your choices of expanding or getting the value of determinant? You can, sorry, what happened? Something is going up this time. Anyway, my final after doing a couple of more operation. Oh, it's here. I don't know what's happening. Something is playing up on system. Okay. My A is this metric. It's determinant 5, 0, 0, 2, 2 minus 1 minus 1, 1. Lucky I wrote that. Okay. I got many ways of expanding this. I can expand it from second column, third column, or third row. Okay. Let's go with the column expansion because we haven't done that. So that will be something new. Okay. So determinant A will be second. So first row, second column, second row, second column, third row, second column, and fourth row, second column. Now, 0 times C12, I'm talking about this, okay? Minus 1 times C22, 0 times C32, and 0 times C42. Awesome. So I'm just talking about C22. Everything else is 0, right? So determinant A is simply minus C22. Now I try to find C22, which is a cofactor of second row, second column. So it's minus 1 power 2 plus 2. And then the determinant eliminating everything. And this is why more number of 0 will help you. But again, it comes with a cost of time. So you have to realize how many more. Can you bring it more easily? If you do 3, 4 more steps, better you obtain more cofactor, right? So eliminate the second row, second column. So 5, 0, 2, 2 minus 1, 1. Sorry, not 2 minus 1, 1. Second row, second column, so even that one is gone. Yeah. So whatever left, 5, 0, 2, minus 3, 0, 0, and 0, 1, 0. So this is plus 1. If I expand it, I mean, again, you can go for expanding it. 502 minus 300010, 50 minus 3001. So that will be 0 plus 0 minus 6 minus 0, 0 and 0. Yeah, simply this is minus 6. I put that up here, minus of minus 6, and determinant is 6. And that's why you have to deal with the familiar metric. And we know the answer was 6. Yeah. So that's it. That's a 4 by 4 expansion. Okay, now we go for one more. Say you got an determinant 2141, 3 minus 121, 1232, and this. If you realize that by adding, you'll achieve something, right? So I added this 2. Doesn't matter where you keep it. Row 1, 2 doesn't matter, right? So what I have done, my row 2 is now row 2 plus row 1. So first row doesn't change, third row doesn't change, fourth row doesn't change, only this one. 2 plus 3, 1 minus 1. So what do you observe? Your 5062, 5062. They are the same row, same or proportionate row should give the determinant value as 0. Simple. So simply by observing the determinant or doing a simple operation, your calculation will be a lot quicker, lot shorter. The shorter and the quicker it is, the chances of error or the typos will be very minimal. Right. Now we talk about something about the rank of a metric. Again, there is that thing which I have it here. That's a link that I wanted to bring up. Yes. Mm. What is the physical significance of rank? So there is a lot of thing that you can discuss. Solution of its rank and everything. So that's a couple of people have explained what is the rank and where you use it. Okay. Right. Let's go into definition. Try to understand it. So consider a metric. Now we are not talking about square metric. For determinant, it has to be square. For rank, it could be any metric. Okay. If A has a rank, so what we are saying, let me put a number to it. Say it's a 5 cross 3 metric. 5 cross 3, 5 rows and 3 columns, right? You can say rank is 3 only if you obtain the third order determinant whose value is non-zero. So you sub-metric, think about the sub-metric of that 5 by 3. So you can become first column, second column, and fourth column, right? Separate that into a sub-metric, obtain its determinant. If it is 0, go for the next. If it is 0, go for the next. But the moment you find at least one of them non-zero, that's it. You say the rank is 3. Okay, so you say that rank is greater or equals 1 if and only if there is a submetric with non-zero determinant. Okay, the determinant of any square submetric with more than r row has a value equal to 0, right? So if you got about 4 rows, then obviously, right, the value will be 0. Okay, same thing said in a different way. So rank will be always the same or smaller of MNN, maximum of MNN. So if it is a 5 by 3, a rank will be maximum 3, right? It will be maximum 3. Okay, let's look at an example. It's a 4 by 4 determinant. Rank will be maximum 4. But this is the same example we just saw, and we know its determinant is 0. Okay. There is only a 4 by 4 matrix for this. Okay. Whose determinant is 0. So rank cannot be 4. So rank can be 3 or smaller. Rank will be 3 only if you find a determinant, non-zero determinant of order 3 by 3. So how many ways can you find, 3 by 3 determinant? So you can pick up this, or this, or this, or there'll be 9 some such possibility. You just have to focus on one of them. If one of them is non-zero, then the rank is 3. You just have to think of one of them. Okay. Okay. Let's pick up something which we think could be non-zero. Say I wouldn't go with picking up second and fourth row because they are the same row. So I know it, that if they are both there, that is not a good choice. I have to think of something else. Okay. So let me pick up. I mean, you can pick up from anywhere, any one of them. So if I pick it up from the original one and call the metric subdivision, there's 1, 4, 1, minus 1, 2, 1, just some random one. Let's call it some metric A and obtain its value. That value turned out to be, I mean, you have to obtain it. 1, 4, 1, minus 1, 2, 1, 2, 1, 4, minus 1, 2, 2, 3. And that value is turning out to be 10. Definitely non-zero. See, if it is 0, you go to the next one. If the next one is also 0, go to the further next, until you have verified all 3 by 3 determinant, right? And if all of them are 0, then only you say the rank is not 3. If you find one of them that is non-zero, simply say rank is 3. That's it. So some of the properties of determinant, which I want you to prove it in your spare time. Determinant of A and A transpose is the same. So pick up a matrix, square matrix, determinant 1, 2, 3. The same example that we have been carrying on, minus 1, 2, 3, or 6, or whatever, and the 7, 8, 9. The same example which we're doing. Obtain its transpose and obtain both of the determinant, and there should be the same. If all rows is multiplied with a factor called lambda, then if you bring it out, becomes the power n. And n is either 3 or 4, whatever is the square matrix. Determinant of AB and determinant of BA is the same unit of determinant A times determinant. Okay, so you go for some determinant A, B, multiply together, that's determinant of AB. Then multiply BA, find its determinant. They'll be same as the individual one. Okay? Right. Okay, so we got one important question that we were discussing, is that why do we need to bring more number of zeros, right? And how does it help? So what I can do here as well, I got an empty slide, I think. Yeah, this slide is empty. So I'll use this to explain something, okay? Or I can go and explain it. The more number of zero helps you, simplifying your calculation, and you will also use it to find the inverse of a metric, which I will cover in the upcoming sessions, okay? So let's say if I go to the example that we were talking about earlier for that 3 by 3, I'll just bring up that up. Yes, let's say I'll use this slide. So let's say I got a metric, oops. Okay, let's say my metric is D, the same metric that we know it earlier, right? 1, 2, 3, minus 1, 2, 6, and 7, 8, 9. And we know for 3 by 3, I mean, you could do the calculation. But what if you wanted to go for the same approach of bringing more number of zeros? How does that help? I'm doing two operations here. My new row 2 will be row 2 plus row 1. Because I got minus 1, if I add the first row, minus 1 plus 1 will be 0. So I got a number of 0. I'm trying to make it upper triangular matrix. That means all the elements below the main diagonal will be 0. Okay. I got 7 here. I got 1. How can I bring more number of zeros? So my row 3 will be row 3 minus 7 row 1. And this is a property second, I think. Yeah, second property, where multiplying by an element and adding to the other row does not change the value, right? So the unchanged value is the first row, 1, 2, 3. This was mine. I'm just adding. Yeah, so 1 minus 1 is 0, 2 plus 2, 4, and this is 9. This is 0. 8 minus 14. 8 minus 14, that's minus 6. And 9 minus 21, that's minus 12. Okay, so I got the first column, maximum number of 0 I can. If I just get one more 0 here, that becomes an upper triangular metric. And following our notion of upper triangular metric, the determinant is simply the multiplication of diagonal elements. So what will I do? I have 4 that I can use, and I wanted to add it to minus 6 to make it 0. So minus 6, the only thing that you can add is 6 to make it 0. From 4, how can you make it 6? So you divide by 2 and times by 3. Okay? Follow my wording again. How do you think, how do you know you have to do it this way? I have this element, minus 6, that I wanted to make it 0. How will it help me? It will convert this into an upper triangular metric. If it is an upper triangular metric, I'll show you it's this on some number of slide. I can show you, where was it? It was over here very early that here, this one. If all the lower elements are 0, upper triangular metric, then the value of the determinant simply multiply the diagonal element, nothing else. Okay, so that's what I'm trying to do, right? Okay, so I got this 2. I just have to get rid of this minus 6. When I say get rid of, I have to make it 0. How can you make it 0? If I can have plus 6. Minus 6 plus 6 will make it 0. Now, what will you use? If I use the first row, then this 0 will be gone. But if I use the second row, then 0 with something with 0 is still 0. Yeah, so I'm only allowed to use the second row. You might think, oh, it's just multiply this by 3 and add it here. And this will be minus 3 or 3, whatever. Yeah, so that will, you are getting a 0, but getting rid of one more 0. So you are at the same place. The only thing you can use is a second row. Do something on a second row to get this. Now, we know it's minus 6. I want to add 6. From 4, how can you get 6? So you divide by 2 and times by 3. So second row times by 3 over 2. Right? My new row 3. new row 3 will be old row 3 plus 3/2 row 2. So the metric D, the first row doesn't change, 1, 2, 3. The second doesn't change, 0, 4, 9. This is 0. This has to be 0 because this is why we are doing it, right? 4 times 3/2. If you want, you can, do it like this. It's perfectly fine to do it like this, at least initially. You go to -6 plus 4 times 3/2. 4 times 3/2 is 6. -6 plus 6 should be 0. You had -12 plus 9 times 3/2. Okay. Once you simplify it, the first row, 1, 2, 3, 0, 4, 9, 0, 0, -12 plus 27 on 2, that will give you 3 on 2. So that becomes an upper triangular matrix. The determinant is 1 times 4 times 3/2, and that is 6. And that's what we had earlier as well. You might be thinking that, the other approach of having 2 more columns and cross multiplying is easier. Yes, it may seem so. But when it comes to 4 by 4, having more number of 0 is a blessing. So this is a technique that you should, understand clearly as well. Okay. Sorry, I should have written something over there, isn't it? So those who are watching it, what is it? We're talking about proving it. I leave it to you guys of proving it. I think it's enough. So just just pick up a metric. Metric A, metric B have lambda is equal to 2, and verify all these 3 properties. Yeah. So first of all, start with A and AT of 10 is, determinant. The first one is very easy. Determinant of A is 1. If you talk about A transpose, you talk about 1, 1, 0, 1. Again, determinant is A. So they are both same. Okay. And then your lambda is equal to, you times it A by 2 and obtain it. Then A times BB times N determinant AB. Just verify all of them, and if any doubt, any issues, just get back to me. Okay? So that's it for today. Thank you very much. Any question, concern, please refer to the recording or whatever we have covered. And if you're still unclear, please get in touch. Happy to help. Thank you. Take care.